Okay, so I want to start with talking about LED composition. But I want to mention something first that will help us in finding the LED decomposition. Sometimes called factorization, which I think the book uses, which is a very interesting fact about type 3 operations in Gaussian elimination. So remember, all the type 3 operations in Gaussian elimination are, these are your lower triangular type 3 row ops. And notice, something to notice is that you can put a matrix into a triangular form. So, i.e. Reduced row echelon, not reduced. Oh, when do you know if it's upper or lower? So just what is the definition, upper, lower, or? Yeah, so here we can talk about that. So upper triangular is when you have zeros in the lower part. So there's stuff in the upper. Yeah, based on where the zeros are. If the zeros are in the upper part, then it's lower triangular. And if there are zeros both upper and lower, then it's diagonal. Sure. So notice that you don't need type 2s. To put a matrix in triangular form. Right. I mean, type 2s are kind of helpful, you know, in solving matrices, solving systems. But notice they're not really necessary, right? We have that kind of general form. So if we ignore type 2s, then our LED decomposition becomes a lot easier, because if you just think about type 3 operations, it actually, multiplying type 3 operations is very easy. So let's just do an example. If we have a 3x3 matrix, there's only maybe at most 3 things you need to do. So in your first step, you would eliminate the entries in the first column. So you would add to row 2, you would add some multiple of row 1, and to row 3, you would add some multiple of row 1. Does that make sense? Like, whenever you're solving a matrix, you always do this step, right? This gets rid of these entries here. So what are these matrices? So for a 3x3, let's say this is E1 and this is E2. What does E1 look like? So 3x3. What's the first row of E1?
2 plus A over 1.
Sorry, I didn't catch that. Were you saying something, or someone's mic is on? Correct. 1 0 0. Right. Only row 2 is changing, right? So that's okay. So the first and the third rows should look like identity. So now what does the second row look like? A10, good. Okay, so let's do the same thing for E2. So what's in E2? So what's the first row of E2? 1, 0, 0, right? That's not changing. What is the second row? Correct. Row 2 is not changing. And then now what's the third row? Yeah, that's supposed to be a B. But yeah, B01. That's your E2. Now what's your, okay, so now this is your first step, right, in your algorithm. You've eliminated all the entries in column 1. So what would you do next? So now that you've eliminated all the entries in column 1, what's your next step? What would your next step be? Yeah, you look at column 2 and there's only one thing you need to eliminate, right? What do you need to eliminate in column 2? Right. All you need to do is eliminate this entry. So that is row 3. You're doing row 3 and we'll do plus C row. And now which row do we use? Row 2, yeah. Let's make this E3. So what does this look like? So first and second rows aren't changing. Now what is the third row? How does third row read? Zero C1, correct. All right, this is E3. So now if you do this, you may not get row echelon form, but you'll get something that's triangular, right? After you do this, this will become something that is upper triangular. Everyone see that? So A, B, and C depend on the matrix, right? But you at least have these 3 steps, and you don't need to do them with type 2s. As of course, this is all supposing that you don't need to do any row swaps, right? But does everyone see that, like at heart, or at the very least, you have to do this? I'm gonna take that as a yes. Okay, so now how do we solve for A? Can someone say how we solve for A? Inverse of E's, yes. So can someone read off? So if U is over here, what's the first inverse we write? E3 inverse. And yeah, so the inverses are just negatives, right? So where does the negative go? So yeah, for these A, B's, and C's. So E3 inverse, you just get a negative C. For E2 inverse, just get a negative B. And E1 inverse, you get to have a negative A there. Okay. So last time we saw that since all of these are lower triangular, this product must be lower. But now let's see what happens when we multiply. And let's kind of do it step by step, and then we can figure out like kind of a shortcut. So let's first do E1 inverse, E2 inverse. So let's think about just these two matrices first. We multiply. And think about the positions of the zeros and ones. What does this being 1, 0, 0 and this being 0, 0, 1 tell you? What does that tell you about the product? You know, these rows that look like identity, what does that tell you about the product? Right, they don't change the first and third row. So in the product, the first and the third row will be these. Will be the first and third row of the matrix on the right. Now look what happens when you think about the second row. Notice that, okay, how about this? What does this tell you? I have a 1, 0 that kind of looks like identity there. What should that tell you about? Yeah, that won't change as well. So, oops. So this is not changing. Now, what is the only thing that is changing? Is we look at, will be the first column, right? So in the first column, notice that there is a 0 here in the third entry, and that will eliminate the negative b part, right? Yeah, thank you. This 0, since this is upper triangular or lower triangular, this 0 will cancel out this negative b contribution. And there's a 1 and a 0 here. So what is the only entry that's left over? Only contribution is negative a. So that's pretty interesting. Okay, now let's multiply E3 inverse. Okay, same thing. Now let's think about actually column operations. What do these things tell you about the product? Yeah, and what so yeah, this means that so the first and first and second column. Well, let's see, the first column will be the same. All right. Let's see, actually the second column is going to change. Oh, I'm sorry. This tells you the first column is going to stay the same. Sorry, I drew the wrong thing. And this tells you the third column is going to stay the same. These are column operations. So now the only thing that is changing is the second column. And if you do the multiplication, right, this would tell you that the first two entries are staying the same. And the only thing that is changing is in this third entry, this negative c. So when we do that multiplication, what's the only thing left over? Negative c. So do you see what the trick is? If you only use type 3 operations, well, look at this product. That's very easy. So if you do row 2 to row 2 plus A row 1, row 3 to row 3 plus B row 1, and row 3 to row 3 plus C row 2, and if this gives you U, then we know that L is equal to negative A, because it's the inverse, negative B, and negative C. Let's do it different. So everyone see that? You don't actually have to do all that multiplication out if we're only doing type 3s. If you only do type 3s, you can easily find L. Everyone see that? See how handy that is? So if we understand this formula for doing row reduction only using type 3, so now we're ignoring type 2s because that could change something, right? Maybe I multiply a row by a number or something, and that might change this very handy formula. So if I only do type 3s, then LU factorization is very easy. And yeah, well, let's use this. Let's use do an example. This is LU factoring of 1, 2, 1, 1, 3, 1, negative 2, 1, 5. Okay, so let's do row operations to get into triangular form as we would do in like 1.1, and then we'll figure out the LU factoring from it. Okay, so give me some steps. What would your first step be? Yep. Row 2 to, and make it interesting, I'm gonna put that there. Row 2 to row 2 minus row 1. And what do you do to row 3? Row 3 plus 2 row 1. Good. So let's see what that would be. 1, 2, 1. Now we have 0, 2 to make it interesting, and then 0. And then row 3, we have 0, so plus 2 row 1. So it's plus 4, and this makes 5. And then plus 2 row 1 makes 7. Okay, now without using type 2s, you might want to use type 2, but let's try not using type 2. What is the row operation you can use? So remember that formula, it's not so nice. Yeah, so it's gonna be negative 2/5, or other way around, 5/2. Right, because you want the 5 to survive. And you want to get rid of the 2. Yeah, that's fine. So we have 1, 2, 1, 0, 2, 0, and 0, 0, 7. Okay, so now we have a matrix that is in upper triangular form. And now let's construct our L. So by our formula that we figured out, we only use type 3s. So let's fill in the blanks. So one thing to think of, to note that when you write out your operations this way, these give you the coefficients in that row. So in row 2, these are the coefficients. There is 1 in the second coefficient, and this is a -1 here, but what would its inverse? If we're thinking about inverses, what would its corresponding inverse be? So what do I put here? +1, yeah, because we're doing the inverse. Okay, so now for row 3, same deal. The coefficients in front of your r's will tell you what to put. So there's a 1 in row 3, so that gets a 1. And now if there's a +2 row 1, when you think about inverses, what should go there? -2. Maybe this is 1. This is -2. And then in our last operation, yeah, +5 halves. 5 halves. And that's it. Okay. Everyone see the application there? So notice I didn't do any type 2s. So it may mess it up. I'm not 100% if it would mess up or not, but only using type 3s makes it guaranteed to work. So it's your L. So that means that we have 1, 1, -2, 2, 4, 1, 1, 1, 5 is equal to 1, 0, 0, 1, 1, 0, -2, 5 halves, 1 times 1, 2, 1, 0, 2, 0, and 0, 0, 7. So that is a LU factorization. All right. So any questions on that? Okay, so that's my recommendation. Only use type 3s, and that will get you through LU factoring pretty easily. All right. All right, so let's talk about determinants. So I'm going to move on to 2.1, finally. This is 2.1 on determinants. Okay, so let's think about the determinant of a 3×3. Okay, can someone remind me, how do you know? Oh, let's think about 2×2. What does the determinant of a 2×2 mean? What does it mean? First of all, what is determinant? So if I have A, B, C, D, the determinant of it. So the 1 over AD minus BC is yes on the outside, but the determinant itself is just AD minus BC. So what does that tell you? For what is that? What do we use that for? Right, whether or not the matrix has inverse. So if determinant A is equal to 0, what does that tell us? Then it has no inverse. Right, and this is because in the formula of the inverse, which we can write, which was 1 over AD minus BC. And anyone remember the entries? Like, what's the first row? D, yeah, the diagonal switch. Yep, swap AD. And then what happens to B and C? Yeah, those get negated. Then they don't swap. So if the determinant is 0, that means that, we can't use the formula. So what happens if it is 0? If it's not 0? Then it has an inverse. Okay, so what we want to do is there a similar formula for a 3×3? All right, so remember, the main idea of the inverse right now, or the determinant right now, is if determinant is 0, then it has no inverse. If determinant is not 0, then an inverse exists. So that's going to be our kind of main definition for determinant for even higher dimensional matrices. So let's think about, when does a matrix have an inverse? So obviously, the first thing is when the determinant is not 0. But if we want to construct a formula, right, we can't really use that as a definition, because so we need to use a different method to determine if a matrix has an inverse, or to describe the determinant. Okay, so when else does a matrix have an inverse? So we talked about a couple other determining factors. Good, when you can do elementary operations to put identity. So another way of saying that is row equivalent to identity. That's going to be the one we're going to use. But and you remember other ones? I'll give you a hint. What can you say about AX equals B? About the solutions? Well, think about it. If it has an inverse, how can you solve for X? It has at least one solution. Yeah, greater than 0. So this will always be consistent. And more importantly, it's always going to be one solution, because you can just inverse both sides. Right, and this is one thing, right? It's not infinite things. So for right now, yeah, these are our main criteria for when a matrix has an inverse. So let's think about row equivalent to identity. Let's just do it. Okay, so row equivalent. So this has an inverse. If it is row equivalent to identity. Okay, so let's imagine that we do this. All right, so first of all, let's suppose A is not equal to 0, because then we have to do a row swap. So let's pretend we don't need to do a row swap. Well, what's your first step? You want to try to put this into identity, row reduction to identity. So what would your first step be? I know they're letters, but pretend they're numbers, and then you could figure out what's your first row operation you would do. Okay, we do row 2 to row 2 plus, not a row 1, right? Because a row 1, that's just a squared, right? So remember, this was, think about our 5 halves. Yeah, negative d over a. So you want to get rid of d, right? So you want to minus d somehow, but there's this a in the way, so you want to divide out by a. Okay, and then what do you do to row 3? So same idea. G over a, yeah. Negative g over a, row 1. Okay, so let's just see what this gives us, and then maybe we can see what this implies. All right, so we have a, b, c on top, and we zeroed out these. Now we have e minus bd over a, f minus cd over a, h minus gb over a, and I minus CG over A. Everyone agree with that? So I'm just going to put in common denominators, but please ask the question if you have it now. So now I'm just doing common denominator. Okay, so now remember, the main goal is to say, does this have an inverse? So let's think about this 2 by 2 matrix here. So let's think about that. So how would you continue? You have to give the row operation, but how would you continue your row reduction to put this into identity? What would you want to do without giving the exact row operation? What would your next steps be? Yeah, I would want to zero out this thing. So the goal is to zero this out. And then what else would we want to do? So think about row echelon form. I would want to put ones on these entries here, right? I would want these. I would turn these into ones. And then what else would I want to do? So suppose you've done that, then what would your next step be? So I've zeroed out that kind of lower left entry. I've done some type 2s to put ones in the diagonal. And then what would your next step be? How would you start the reduced row echelon? So let's just pretend we have that. Yeah, you want to zero out the tops. So blah, 0, 0, 0, 1, 1, blah. Right, then you would zero out the tops. So in particular, you'd want to zero out this entry, right? You agree with that? That would be one step. But what is that? What type of matrix did we just imagine that would be in our future? What matrix is that? In the red box, in this 2 by 2. what in particular, what kind, it is a diagonal, and diagonal full of what's on the diagonal? 1. What do we call that thing? What do we call a diagonal matrix with all ones? Identity. Interesting. So the next step is to turn the 2 by 2 into identity. That would be your next step. So what happens if you can't do that? What happens if you can't turn the 2 by 2 into identity? No inverse, yeah. What would it look like? Do you know what let's try, if you try row reduction, and if you can't put it into identity, what does it look like, a 2 by 2? Yeah. If you can't put into identity, it's supposed to be identity. I'm just gonna put id. Then you get a 0 row. So what does that imply about the 3 by 3 as a whole? If you get a 0, 0 in these bottom 2 entries here, what does it tell you? The whole thing doesn't have an inverse. So is it safe to say that the determinant of this 3 by 3 must depend on the determinant of this 2 by 2? Does that make sense? So the 3 by 3 matrix has an inverse if this resultant 2 by 2 has an inverse. Correct. So we can turn our 3 by 3 problem into a 2 by 2 problem. Everyone see that? So, well, we know what the determinant of a 2 by 2 is. So let's do that. So I'm going to just rewrite the whole matrix on a new page. It's a G. So this has an inverse if AE minus BD. So what is the determinant? Over A times IA minus GC over A minus FA minus DC over A, HA minus GB over A is not equal to 0. So if, then it has an inverse. That make sense? So this is the determinant of the 2 by 2. Okay, cool. So let's do that. All right. first of all, we can take out these a's, right? So they go 1 over a squared. So I'm just taking out the denominators, and now we're going to FOIL out the numerator. So I have a squared ei minus aegc minus bdia plus bdgc. This looks complicated, but I swear we can make this nicer later. Minus fha squared minus fagb minus dcha plus dcgb. Okay. I'm just going to rewrite it, and then we're going to try to first of all, can anything cancel out here? Look at all these terms. Does something cancel? I know I kind of rearranged some of the letters, but is there a pair of, the BCGC thing, right? These cancel. Yeah. Now, of the result, is there a common factor of the common result, of the result after cancellation? The A's, yeah. Everything has an A. So I'm going to just go ahead and take that out. So we have AEI minus EGC minus BDI minus FHA plus FGB plus DCH. Okay, so now for reasons we'll talk about later, let's group the first row elements. So meaning I'm going to group the A's together, I'm going to group the B's together, and I'm going to group the C's together. So I have AEI and FHA. So it's going to be A times EA minus FH. Now let's group the B's together. Let's see, there's a B here and there's a B here. So that is FG minus BD. Oh, no, not B. Factoring that out. Minus DI. And now I'm going to group the C's together. So this is plus C times DH minus CEG. Everyone agree with that? All I'm doing is grouping the things in the first row. Okay. Now let's look at the original matrix and let's see if the 1 over A. Now, if we're thinking about determinant, this 1 over A doesn't really matter, right? That won't affect it being not 0. Would you agree with that? This does not affect the term being 0 or not. Do you agree with that? No, A can be whatever it can be, right? Yeah, and we assume in the beginning that we couldn't do any of this if A was equal to 0, right? We couldn't do this first step. Correct, yeah. So when we're coming up with a determinant formula, we can just omit this. The 1 over A came from factoring out the A. We had a over A squared. We factor out an A. Right. So when we do the determinant, we're not going to consider that part, the 1 over A. This is the only thing that affects it being 0 or not. Only thing that affects equals 0 or does not equal 0. So let's look at our first original matrix and see if there's anything about this formula that that we can see. C, D, E, F, G, H. All right, let's look at this first term. Okay, EI minus FH. Is that special in that matrix? Think about doing EI minus FH. We'll really stare at that matrix. So EI minus FH, that's these terms, right? So yeah, EI minus FH is the determinant of that mini matrix. Correct, yeah. So this is our formula for the determinant of the 3 by 3, and it only depends on 2 by 2 formulas. So this is this EI minus FH is equal to the determinant of this like sub matrix. Okay, what's another one? What's DH minus EG? The 2 by 2 on the left. DH minus EG is determinant of this 2 by 2. And the weird one is FG and DI. But where did those come from? Yeah, it's kind of like a 2 by 2, but it's these. However, just like if I do DFGI, is that the determinant? Is FG minus DI the determinant of that? So look at a bit closer. FG minus DI. It's close. It's the opposite, yeah. So why don't we just write the determinant is A times EI minus FH, and we're going to factor out a negative, minus B times DI minus FG, and then plus and DH minus EG. So FG minus DI equals the negative of this determinant. Okay, so everyone see that and agree with that? Okay, you don't need to do all this proof, but do you agree with that? So this all came from knowing that inverses exist if they are row equivalent to identity. So all we just did was we constructed a way to say that a formula that we already have as the determinant, that this 3 by 3 has an inverse dependent on this determinant of this kind of result in smaller matrix. And we came up with this formula. Now, the remark that that these things in parentheses are determinants of the smaller matrices will make this formula a bit nicer. But so does that everyone agree? Everyone see that? All right, so let's think of a better way to kind of see these see the whole formula. Yeah, the negative part, I just wanted the thing inside to be the determinant. So this is a determinant, this is a determinant, and this is a determinant. Before we had a negative determinant. The stuff inside the parentheses was a negative determinant. So yeah, I just want to take it out. So everything in parentheses will be a determinant. So I had to take out the negative to do that. Okay, so we are going to define a couple of terms to make this a bit easier to talk about. All right. Make sure I get the right definition. Okay. The minor of a matrix. It's the minor of an element. So we're going to call, so if this is my matrix here, M11 of A will be defined as, okay, so let's say A is n by n. The minor, maybe 1, 1 is going to be the dimension 1 less that is obtained by deleting the first row and first column. So, for example, if I want to think about M11 in this matrix, it would be, well, here's 1, 1, and I'm going to delete entries in that row and in that column. So what's left is E, F, H, I. Everyone get the concept? So 1, 1, we look at the entry 1, 1 and delete all the entries in that row and column. So M, like what would M 1, 2 be? So I look at entry 1, 2. Or let's do 1, 3 to make it easier to look at. So I look at entry 1, 3, and I delete all entries in that row and in that column. Right, so 1, 2 would be what you said, would be D, F, G, I. Yeah, and then 1, 3 would be D, E, G, H. Yeah, so 1, 2, and I just read out what's left over, D, F, G, I. Everyone get the concept there? So what would M22 be? So I look at 22 and I delete all entries in that row and in that column. A, C, G, I, correct. Okay, so we're going to define the determinant of the 3 by 3 using the determinant of these minors. So if A is 3 by 3, then the determinant of A is going to be, so let's just read out the formula using the one that we found here. A, B, and C are the elements in the first row. So it's going to be A11 times the determinant of EI minus FH. What minor is that? Or sorry, the matrix EFHI is the minor 1, 1. Yeah. So we have A11 times the determinant of M11. Similarly, but now we have a minus because that's what we found out in our construction. A12, and then what is DIFH? What minor is that? One, 2. So that's a pretty nice formula. And then we have A13 times the minor of 1, 3. So very nice. So that's our formula. Can someone give me a sum definition of this? Oh, actually, why can we just disregard all other submatrices? I'm not disregarding them, right? I'm just re-expressing the formula that we found here. This is our formula that we found. Using determinant of submatrices like A, B, D, E. It turns out that we can create a formula that would use A, B, D, E. But this is our kind of intuitive constructions based on like kind of what we've been doing. It turns out that you can do this with elements in any row. So in this case, we did the first row, but it turns out it's also true if like you can do like 2, 1 times minor of 2, 1, 2, 2 minor of 2, 2, 2, 3 minor of 2, 3, but the negatives might be different in that case. There might be other negatives, which we'll get to later, but the most intuitive way to approach it is just using the first row. But we can do that. So can anyone see a problem with constructing a sum notation about this? This like begs a sum notation, right? With all these indices. The negative, yeah. So let's think about that. Can anyone think of a formula? Where we have, correct, yeah, it's going to be -1 to the n. So if I have the sequence 1, -1, and 1, yeah, so it's going to be, if you do -1, but to the n wouldn't work, right? Because to the n, that would make that 0, yeah. So we could do m+1, but for yeah, for right now we can make that our formula. But I'm going to propose a different. Actually, we want to delete that. Different formulas will be used later. So when it's using the first row, we don't have another formula. When we're using the first row, we can use k equals 1 to 3, -1, k plus 1, a1k, determinant of m1k. Okay. So that's our formula. That's our determinant formula. Since it's 3 by 3, you don't need to memorize the sum. But later we will, when we do n by n, we will use some sort of sum notation. But this is just to kind of tease us for the general notation. But everyone, any questions on that formula? We'll do an example. Okay, so let's do one. Let's just do that one. Let's find the determinant. Okay, so what do we do? Based on our formula, it's a11 determinant of m11 minus a12 determinant of m12 plus a13 determinant of m13. Okay, what's a11? One. What is m11? Five, 6, 8, 9, right? Delete the first row, first column. So minus, so a12 is 2. And what's m12? Four, 6, 7, yeah, 7, 9. And then we have 3 times the determinant of, and what's m13? 4, 5, 7, 8. All right, let's do it. Okay, what is the determinant of this 2 by 2? Want to give me the subtraction rather than the answer. Like, what is the? So you don't have to, yeah, so 45 minus 48. So this is 45 minus 48. And we have minus 2 times, and what's the determinant of this? At 36 minus 42, and then plus 3 times, and what's the determinant of this? Yep, 32 minus 35. All right, so let's calculate this. What is that, -3? What is that, -6? And then what is that, -3? So I have -3 plus 12 minus 9. And what is that? 0. What does that imply? Has no inverse. So this matrix does not have an inverse. Do you remember what that is called? What do you call matrices that have no inverse? Good. This matrix is singular. Okay. Everyone get the idea? Okay. Let me do one more maybe. Question? Why is it 45 minus 48? Oh, it's 5 times 9 minus 6 times 8. Yeah, you do the product of the diagonal and then minus the product of the off diagonal. So it's AD minus BC. Yeah, okay. Let's do this one. Okay. Okay, what do you think we can do? So does the first minor matter here? No. So it's 0 times M11, but that's 0. So now let's do minus 1 times M12, well, determinant. Well, we can still continue. It's just going to be, it's just 0 times it. Oh, I did. Okay. Because I said that, because I don't want to get into why, we can still talk about that. Let's do that one instead. The idea is that, well, let's see what happens when we do this. So let's do 1 times M11. And then minus 0 times determinant of M12 plus 2 times determinant of M13. So the idea about why A11 can't be 0, that was in our construction. But if it was 0, then you could row swap, was the idea. But I do agree that in the construction, there wasn't a, we haven't discussed how row swapping affects the determinant yet. So I agree, but next time I'll talk about that. But so let's pretend that A11 can't be 0 for this to work. Okay, so what's M11? (0.406), so minus 0. And what is M13? Oh, M12, it doesn't really matter because we have 0 times it. So I just skipped that one, but that is true. 5476 would be that. Yeah, so M13 is 5070. Okay, what are the determinants of both of these? Both of them are 0, correct. Now, can you let me ask you, did that even matter? Correct, yeah. It didn't matter that we had 1, 2, 5, 4, 7, 6 there, right? They could have been A, B, C, Ds, right? So I mean, I'll leave it to you to, you do, if the third column is all 0s, I would, you should check that out. Yeah, so this is 0 and this is 0. So right now, if the second column at least is all zeros, then the determinant is equal to 0. How else can you know this? Correct, yeah. Without the determinant, without this formula, could you figure out why the determinant is 0? What does a row or column full of zeros tell you? So before we even discussed a determinant, exactly, yeah. If you were to try to put this into reduced row echelon form, you could never get identity. So you could just say that. This will never be row equivalent to identity. Okay. All right. Any questions on any of this? Okay. One thing. Let's actually think about row swapping. We have a little bit left. So we have that the determinant will be. Well, let's do 2 by 2s. How row operations affect the determinant. So let's start with 2 by 2s, and this will be the last thing we'll do. Okay. If I have A, B, C, D, what's the determinant of that? AD minus BC, that's our formula. Now, what happens if we row swap? So we have CD and AB. What's the determinant of that matrix? CB minus AD. What's the relationship between AD minus BC and CB minus AD? So what do you mean swap positions? What's another way of saying that? Negative, yeah. One is the negative of the other. Row swapping for 2 by 2s, we'll do the same thing for 3 by 3s. Row swapping negates the determinant. Okay, so we're out of time, but I just want to leave you with that. And it's something you can easily do. Try to figure out what type 2s do, and then try to figure out what type 3s do. And so maybe I use this operation maybe. So use one of those and see what happens to determinant, and then do this and see what happens to determinant. This one is the most interesting, I think. Do either one. It's something and they're only 2 by 2, so these aren't bad, but good practice for next time. Okay, so I'll see you Monday. We'll likely finish 2.1 Monday, and then our test will probably be the Monday after that. Is that okay? So So we have Monday, this coming up Monday, and then a week after that will be the midterm. Oh, okay, I'll stop.